Hello, class, and welcome. We are now at the last stretch of our um, course, and this will be the last video that you're going to watch. And this video will cover correlations and non-parametric tests. So let's begin. The main tenets of correlation statistics are the following. Correlation statistics will give you a sense of the strength and direction of an association between two variables. Now, take note, what it says here is association. There are two major purposes of doing research. That is, one is to establish association, and the other major purpose is to establish prediction or predictive power. Correlation statistics are basically limited to determining strength and direction of an association between two variables, nothing more beyond association. The other important tenets of the other important tenet of correlation statistics is that we also must set the p-value to equal or lesser than 0.05 in order to provide the mathematical calculation for statistical significance. Or in other words, this is the significance level that we must um, establish when using correlation statistics. You might wonder, isn't it that we always have 0.05 for almost all test statistics? You might be surprised, but the answer is actually no. There are experiments where we could say that our significance level is at 0.10. But again, when you are using correlation statistics, this is a requirement. You cannot lower the significance level than 0.05. So what are correlation coefficients then? Because this is obviously what we are going to get when we run correlation statistics. Well, the term correlation, we use this very often in our day-to-day language. Um, we always say, um, well, bigger heads is correlated with higher IQ. So what we mean is that if you have big heads, you probably have a bigger brain, and that's why you also have higher IQ. So that's what correlation is, that we're making an association. Now, in statistics, correlation concerns a specific type of relation that is measured mathematically, and you get the correlation coefficient. The coefficient, based on the value of your coefficient, it gives the researcher a sense of the measurement of the strength and direction of an association between two variables. Now here again, you have to remember here in correlation, coefficient, and correlation statistics, there are two variables, only two variables. When you start putting more variables, then you have to move on to another statistics, and that will not be covered in this course. But another level of statistics, such as your multivariate regression analysis, and other sophisticated statistical tests can simultaneously examine the associations of 3, 4 variables to the dependent variable. So that is a very basic rules in terms of correlation coefficient, is that there's 2 variables. We're limited with that, and it gives you a measurement of the strength and direction of association only, not prediction. So the reason why I'm emphasizing this, because when you are ready to make a conclusion of your study findings, if you are using correlation statistics and correlation coefficient values, then your conclusion has to be all about strength and direction of the association between 2 variables. So what are the types of correlation coefficients? Well, as I mentioned, it's all about measuring the association. And the first one, the first type, is the Pearson. Remember Carl Pearson, who also developed the chi-square statistics? Yep, he's very bright. He's again the guy also who developed the Pearson correlation coefficient to measure the association between 2 variables. Pearson is a parametric test, and the minimum requirement for Pearson is that the 2 variables must be at the interval or ratio scale type of data. If they are not interval or ratio type of data, then you can use the non-parametric equivalent of Pearson, and that is the Spearman's correlation coefficient. Both Pearson and Spearman's correlation statistics actually measures the association of 2 variables. But the difference here is that Pearson is for parametric tests and for variables that are at the interval or ratio scale type of data, whereas your Spearman, it's non-parametric, and the type of data could be at the ordinal, interval, or ratio. So what you will see in a lot of publications in social sciences that uses the Likert type scale, I think that you will see, if they're interested whether an independent variable is associated with a dependent with another variable, and they are using the Likert type scale, and we know that that's ordinal, which means that both the researcher and the respondents are not exactly sure about the distance between the values in the scale. So that's ordinal, and so we would expect that the researcher would use the Spearman correlation statistics if they are using the Likert type scale questionnaires. So here are hypotheses for our correlation statistics. Very simple, because we are just looking at 2 variables, and so our null hypothesis would simply say that there is no correlation between the 2 variables, and that would mean that the R value, or the Pearson's R, if it's parametric, is basically 0. And the alternative hypothesis then is that there is correlation between the two variables, and that is represented by the R value that is not equal to 0. So 0 is a very important concept in correlation, and let me demonstrate that to you in the next couple of slides. So as I mentioned earlier, correlation statistics will measure the strength and direction, and the correlation coefficients are denoted by R, and I mentioned earlier 0 is a very important concept in correlation coefficient. Why? Well, because 0 indicates no correlation. So that's where you start. No correlation is 0. So the value of the R can fall as low as -1 and as high as +1. So those are the only numbers you're going to remember when it comes to correlation coefficients values. Where they are when it's -1, it means that there is a perfect negative or inverse relationship between the two variables. Putting it in another way, it means that as one variable increases in value, the other variable decreases, because that is what you call a negative or inverse relationship. Well, what about if the R is +1? Well, that means that there is a perfect positive relationship. Simply put, if one variable increases, the other variable also increases because there is a perfect positive relationship. I've already discussed what 0 means. It means that there's no relationship, there's no association between the two variables, and that is where we start. And then it is prudent then to say that the closer the correlation coefficient is to the 0 value, then the weaker the association exists between the two variables. Let me demonstrate this. Here is a Venn diagram, and what you can see here is that the square of the correlation coefficient, which is R squared, will tell you how much variation is shared by the two variables. If you look at the shaded area in the middle, that is the shared variance, or what we call the R squared, between variables A and variable B. And the clear area shows the unique variance of each variable. So when we plug in values then, if it is important that we look at the scatter plot first before we start looking at the correlation coefficient values. Why? Well, because by just looking at the scatter plot, it gives you a sense already whether there is a positive correlation or whether there is a negative correlation or whether there's no correlation at all. So what we have here in our slide is a demonstration of a scatter plot in a sample where there was no correlation between the two variables. Well, here is another slide of scatter plot that shows you perfect positive correlation where the correlation coefficient, which is your R, is equal to 1. Well, think about here in the x-axis right here. Supposing our x-axis is income, and then our y-axis is basically the IQ of um, of our respondents. And so we're trying to find out, is there a is there an association between the income and IQ? So, you wanted to know if you are intelligent, perhaps you will be hired with better jobs and better salaries. So you're trying to test that um, research question using correlation statistics. So if your x-axis here is the income, is showing that as your income increases, so these are our scatter plots, as your income increases, your y-axis, which is representing your IQ, also increases. So you can see here, if your income supposedly, let's put this as 2.5 in thousand pesos. So your 2.5, as it gets to 10,000 pesos, what we have seen is that the IQ, so obviously this is not IQ because it's 2.5, 5, 7.5, and 10. So you just use your imagination that supposing this is an IQ in the y-axis starting at 80, then 90, then 100, then 110, 120 to 130. And as your income increases, it also shows that the IQ also increases. And that's what we call perfect positive correlation. What about the opposite one, the perfect negative correlation, when we have a Pearson, a correlation coefficient value of -1? I'm trying to avoid Pearson or Spearman because we are not yet talking about what type of variables we have and whether it's parametric or non-parametric. So anyway, let's go back to the question of how does the perfect negative correlation scatter plot looks like. Well, right here, supposing we're using the same question, is the IQ correlated with income? And again, here on your x-axis is your income, and someone's income was like around here is 10,000, but as the income decreases, it becomes 7.5, 7.5 thousand, 5,000, 2.5 thousand income. Let's say that 2.5 thousand pesos. As you can see, as the income actually decreases, look what happened to the IQ. The IQ actually increases. So this is what you call a perfect negative correlation. So what type of research question can correlations help to answer? Well, let's say that we are interested in trying to see association of screening tests at the start of the class um, to the final numerical grade. So at the beginning of the statistics class, we're going to give a screening test, and then we look at and tabulate and plug them all the scores in SPSS, scored from 0 to 100. And then at the end of the statistics class, we're gonna also assign, obviously, plug in the final numerical grade of everyone in that class. And the question would be, how could we tell if this screening test was any good in terms of association? Can we say that those who scored very high at the screening tests is highly associated with a higher final numerical grade? So what we can do is do correlation statistics. So right here, we need to know now whether we're going to use Spearman or are we going to use Pearson. Oh, I mean, Spearman and Pearson correlation coefficient values are interpreted in the same way, but they have very different rules. So what were the rules for Pearson? Well, Pearson has to be parametric. And so if and then Pearson also requires that the variable must be at the interval or ratio scale type of data. And in our example here about screening tests, our dependent variable, which is the final statistics grade, is a ratio data because it has a zero. It has a natural zero point. I mean, it's from 0 to 10 if we're going to assign 0 to 10 numerical final grade. And then our independent variable, the screening test score, is also ratio because the lowest score could be 0 and the highest score could be 100. So knowing that both are ratio type of data, are we going to use Pearson or are we going to use Spearman? So here's some more data, type of data and assumption that we need to remember when we are about to decide which of the correlation statistics we're going to use. So this is something that, I actually put a cheat sheet on my lab gown just to be sure that I don't make a fatal error in selecting my statistics when I'm doing my analysis of my data. So again, for Pearson, the two variables are either interval or ratio, and the two variables are normally distributed. The two variables are related to each other, so some kind of a linear fashion, and that there should be no outliers in your data when you do Pearson correlation because that outlier could definitely significantly change your correlation R value. Um, what about Spearman? Well, Spearman, both of the variables can be ordinal, interval, or ratios. As I've said, Likert type scale questionnaires, lots of social sciences, lots of construct that nurses are very interested to measure, like stress and anxiety and sleep. I think we use a lot of Likert type scale questionnaire for those to measure those constructs. So if you start examining associations with other variables, you need to choose Spearman correlation statistics. The other rule for Spearman is that variables need not be normally distributed. So obviously this is non-parametric if it does not require normal distribution. And then the other rule of Spearman is that the two variables are related to each other in a monotonic way. What does that mean? Well, one example is that the direction of the relationship does not change, but not necessarily linear either. So just it doesn't change. It's monotonous voice. It's the variables, the characteristics of the two variables are monotonic. Um, so it does not uh, change. The direction of the relationship does not change between the two variables. And then the last one is that the Spearman test is actually less influenced by outliers. So going back then to our screening test variable and our final numerical grade in statistics, how what type of correlation statistics are we going to use? Is it the Pearson? Is it the Spearman? Well, I think the answer is very clear that we're going to do Pearson. All right, so when we do correlations, there's 6 steps. We state the hypothesis, we define the significance level, make sure the data meet all the necessary assumptions. We look at the scatter plot of the two variables. Then we obtain the correlation coefficient value between the two variables. And then we determine the statistical significance. We state a conclusion. You either reject or accept the null hypothesis and basically make a conclusion from your results. So to illustrate the 6-step procedure, is the screening test positively associated with the final statistics grade? To answer this question, we will use data from the 10 graduate students. Each student took the screening test before starting the statistics class, and we have the measures of the dependent variable, which is the statistic grade ratio type of data, and then the independent variable was the screening test score, which is also a ratio type of data. The hypothesis, again, the test scores on the screening test are not correlated with the final statistic numerical course grade, and that is represented by an R value of 0. The alternative hypothesis is stated as the test score on the screening test are correlated with the final course grade. So your R does not equal to 0. That is your alternative hypothesis in a correlation statistics. Then we define the significance level. Remember the tenet of correlation, it has to be at 0.05, and we need to do two-sided. Why? Because we do not know the direction. So it can go positive correlation, it can also go negative correlation. So when you do correlation statistics, you have to put your alpha level at 0.05 using two-sided tests. If you put one-sided test, you must have a very strong a priori study that gives you very, very high assurance that you know exactly the direction of the experiments that you are performing. And the next one is that we calculate the degrees of freedom, and in correlation It's very simple. Degrees of freedom is just equal to 2 less than the number of subjects. So for our case, we have 10 graduate students. We subtract 2 and our degrees of freedom is 8. So that is the formula for the degrees of freedom for correlation. What about the critical value? Well, to find the critical value in the Pearson correlation table for a two-tailed test with 8 degrees of freedom, of course, SPSS will give this to you. The critical would be at 0.632 for two-tailed with 8 degrees of freedom. So, if our calculated correlation coefficient, which is represented by R, is greater than our critical correlation coefficient, then we will not accept the null hypothesis. We will reject it. And of course, SPSS will do the magic for you. But just like your chi-square distribution table that has the critical values using the degrees of freedom, Pearson's correlation statistics also has the critical values called the Pearson product moment correlation coefficient critical values. So in our example, we have degrees of freedom of 8 and our significance level was at 0.05. So what anything below 0.632, I'm sorry, anything above, because we're talking about critical values. So right here, this is the 0.05 significance level for two-tailed, and our degree of freedom is 8 because it's 10 minus 2. And therefore, if we get an R, or what we call the correlation coefficient value of 0.632, anything higher than that are all going to give you very highly statistically significant association between the two variables, because you're now moving to the 0.02 and the 0.01 level of significance. So right here you're at 0.632. As you get higher and higher and higher, then you know that your significance level also gets very higher, and then you will reject the null hypothesis. So check that all the data meet all the assumptions. There are two variables. The two measures are normally distributed, and the two measures are interval or ratio. Check. We all check that for our example on the screening test and the final numerical grade in statistics. And then the last one we need to check is that the two variables have a linear relationship. So we have to check the scatter plot. And it looks like we do. So, and also if we draw a straight line then closest to where the values are in the scatter plot, then that also gives you the direction. In this case, it looks like it's the direction is to the right, and therefore that is a positive correlation. If you draw an imaginary line from here all the way there, because that's where our data points are, then we know that the direction is positive, because remember the direction is negative if the line goes like here, but our data points don't align to a negative correlation line. So for this example, we know that this is a positive direction, and here is our correlation coefficient. The calculated correlation coefficient is 0.617, and our R squared is 0.38. And look at our two-tailed, and what is the p value? It's 0.057. So are we going to accept or are we going to reject the null hypothesis? Well, clearly this is higher than 0.05. It's not less than 0.05. So we are actually, we cannot reject the null hypothesis because our significance level is not statistically significant. So the correlation between the screening test and the final statistic rate is 0.617. However, the p-value is greater than 0.05. So this correlation is not statistically significant. All right. Now, a few words here. This is the last slide. There are other types of correlation. The first one is called the pi, and you will see this on SPSS. The pi is a correlation statistics that assesses the correlation of two dichotomous variables. So what are your dichotomous variables? Well, typically, again, male, female. It comes to income, high income, low income. So just two dichotomous variable. That's you will use the pi correlation statistics. And the other statistics is called the point biserial, and that is a statistics that's being used to assess the correlation of one dichotomous variable with one continuous variable. So for example, you have a dichotomous variable that's male or female, and you use one of that dichotomous variable, and then your continuous variable would be IQ. So you are going to use point biserial if you want to do correlation for that. The next one is the Kendall's tau. It's a non-parametric test of correlation that can be used as an alternative to Spearman. But I think Spearman is quite very popular. I seldom see statistician using Kendall taus, but that is again an alternative to Spearman. You can use the Kendall's tau as well. And the second to the last is the contingency coefficient. This is a non-parametric statistics to assess the association between two nominal variables. So think about this. This is nominal now. A nominal is just name, just like name of schools, name of bank, and then, again, it's non-parametric and it's called a contingency coefficient if you want to know whether there is a correlation between two nominal variables. Who knows? You want to know, is there a correlation of, let's say, a nominal variable bank for Citibank, and then when it comes to another nominal variable who are studying in the most expensive school, let's say Cebu Doctors. So if you want to examine the association between these two nominal variables, the name of the bank and the name of the school, and then because you have some kind of hypothesis that they are correlated or they're associated, then you can do your contingency coefficient because those are nominal variables. And then the last one here is the universal measure. It's on SPSS, it's you'll see it as a ETA. This is a correlation statistics that's used to measure relationships that are not monotonic, such as uh, direction changes for the different values. Um, this is quite rare that you're going to have a variable where the direction changes for different values. And um, I still have to find an article that really utilizes this universal or ETA type of correlation. And when I do, I'm gonna share that to you. But it's I have not encountered a study that have used a universal measure or ETA correlation statistics. All right, so that would be the last slide and also my last video lecture for this course. And well, I guess as they say, don't say goodbye. We just say so long. And um, we famously say here in America, do good things. All right. Take care, class. And if you have any question, feel free to email me, Viber, or FaceTime. Take care and good luck on your final exams. And I will be posting the group work number 4 so that you will have good practice just prior to your final exam on the 22nd of August. Take care. Bye bye.